Hey guys, I'm going to teach you how to use z-scores. So before we jump into them, let's talk about why do we actually need them? Like, what are they used for? So before this point in time, you should know how to use the empirical rule. So what z-scores are going to allow us to do is they're still going to allow us to calculate percentages of data that fall above a point, below a point, or between 2 points. So it's still going to accomplish the exact same thing the empirical rule does. It's going to give you percentages of data that fall between points. The only difference is the empirical rule is a little bit outdated. Okay. The reason for that is the empirical rule can only help you out if you fall exactly at 1, 2, or 3 standard deviations above or below the mean. So if you do that, great, the empirical rule will work. But let's say you're trying to find, I'm not a full standard deviation above the mean, I'm like a half standard deviation above the mean. The empirical rule no longer works in that case. So that's where z-scores come in. Z-scores are still going to accomplish everything the empirical rule does, but it's going to do more. Okay, so it does everything the empirical rule does and more. The last thing that z-scores are useful for us is z-scores are also going to allow us to compare things that traditionally we cannot compare. And I'll show you through an example what I mean by that. Okay, so the first thing I want to do is just talk about, here is the z-score formula. So what we're going to do is z equals x minus mu divided by sigma. AKA, you're going to take some value and subtract off the mean and divide by the standard deviation. That is going to give you a z-score. So another way that you might hear me say this is the observed value minus the expected value divided by the standard deviation. So x minus mu divided by sigma, or x minus the mean divided by the standard deviation. So the first thing I want to do as an example is I want to talk about how do z-scores allow us to compare things. So the example I have here is Ben scored an 82% on his biology final, and it's missing a piece here. We should say that the scores were normally distributed with a mean of 79% and a standard deviation of 4%. I left out the normal distribution piece that is needed here that allows you to do the z-scores. Same idea with the empirical rule. You need a normally distributed set of data before you can do it. Jerry scored in 78% on his algebra final. That should again say scores are normally distributed and have a mean of 74% and a standard deviation of 3%. Who did better? So did a little poorly here writing out the question, but we'll make do. So we're assuming the scores are normally distributed. Ben scored an 82% on a test that had a mean or an average of 79 and a standard deviation of 4%. Jerry scored a 78% on a final that had a mean of 74 and a standard deviation of 3%. So what we want to know is who did better. Did Ben do better or did Jerry do better? So a lot of people that don't know how to use statistics and know how to use z-scores would probably just straight up compare that Ben scored a 82%, Jerry scored a 78%, therefore Ben must have done better than Jerry. That's not exactly true. We need to factor in the means and standard deviations here as well. So what I'm going to do is I'm going to calculate a z-score for each of them. So I'm going to calculate a z-score for Ben, and I'm going to calculate a z-score for Jerry. Once we have a z-score for each, we can compare them. So we can't straight up compare them because Ben took a biology final and Jerry took an algebra final. So right now they're not on the same playing field, but a z-score will get them on the same playing field so that we can compare the two. So again, the z-score, we're going to take our observed minus our expected divided by the standard deviation. So we know the mean for Ben's test was a 79. So we're going to subtract off 79, and his standard deviation was 4%. So I could fill in the mean and the standard deviation. All we need to fill in is what was the score that Ben got? Well, Ben got an 82%, so that's going to go here. We're going to take 82 minus 79, then we'll divide by 4. So 82 minus 79 is 3. 3 divided by 4 is 0.75. So Ben has a z-score of 0.75. We're going to do the exact same thing with Jerry. We're going to calculate his z-score, and then we're going to see how do their z-scores compare. So for Jerry's algebra final, they had a mean of 74, so I plugged in the mean. Standard deviation of 3%, so I plugged in the standard deviation. Jerry's observed score was a 78, so observed minus the expected divided by the standard deviation. So 78 minus 74 is 4. 4 divided by 3 is 1.33. So Ben has a z-score of 0.75. Jerry has a z-score of 1.33. So all we need to do is, now that they're both on the same level, they're both on z-scores, we just need to talk about, well, who did better. In this case, for final exams, a higher score is better. So in this case, a higher z-score is better. Since Jerry's z-score is bigger than Ben's z-score, Jerry did better. So Jerry did better. So that was a quick and easy way for us to compare who did better just by using z-scores.
Way to go, Jerry.
So what I'm going to do is now I'm going to calculate some probabilities using z-scores. So kind of the same idea of what we did with empirical scores. We're going to figure out what percentage of data falls at different spots. So the example I have is the average amount of weight a basketball team can bench press is 245 pounds with a standard deviation of 8 pounds. And what I should have added here is this is normally distributed, because without that we actually cannot technically do z-scores. Minor detail, but let's attend a little bit to precision there. What I want to figure out is I need to find the probability a basketball player can bench press, and then in option A, 240 pounds or less. So I want to figure out the probability that a player on this team that can bench press 245 with a standard deviation of 8, they can lift 240 pounds or less. So what we're going to do is we're going to do a z-score. Okay, a z-score. We're going to start with that, and then we'll introduce how the probabilities relate here. Also in this scenario, we're just going to assume this is like their max bench press. So the max bench press is 245 pounds, standard deviation of 8. Because I know some people will say, well, wait a second, can everyone do this? It's just a basic example, guys. So what we need to do is observed minus expected divided by standard deviation. So the observed is going to be 240 pounds. What we expect is the mean, which is 245 pounds, and we're going to divide by the standard deviation of 8. So we got to take 240, subtract 245, so that's negative 5, then divide it by 8. I'm going to round this to one decimal place. Negative 0.6 is the z-score. Okay, so what we're going to do, and in your note packet, you're going to have a standard normal table or a z-score table. What this table does is it's going to allow you to look up z-scores and figure out probabilities. The key is these tables always do the area below. So it's always going to give you some point in below's area. It never tells you the area above, which is fortunate here because we're going to find 240 pounds or less. So it agrees with this. This table is only going to do less. So what you're going to do, and I know it's hard to see on the stream, but you guys have this, should have it in front of you, is my table only does 1 decimal places. There's tables out there that do 2 decimal places. I'm going to look up this z-score. So negative 0.6. So I go in the negative column all the way down to negative 0.6, and I see 0.2743. 0.2743. So a way to visualize this, kind of what the empirical rule is, really we're looking at this point of 240, and we want to know how much percent of my data is in that area or below. So what we did is we calculated the z-score for this point, and we looked it up, and the z-score table is going to give you this area always to the left, always the area to the area below. When you look up negative 0.6, again, we had 2743. So 0.2743. So we just got to convert that to a percentage. So 27.43%, because this is a proportion. changing it to a percentage, is 27.43% are going to lift 240 pounds or less. Okay, so another way, if you didn't know how I jump from proportion to a percentage, multiply this by 100, you'll get there. So a little bit tougher examples here. I want to know what's the probability that I do 260 pounds or more. Okay, so we're going to start with z-scores, then we're going to look it up in the table, then we're going to get our percentage. So starting with a z-score, we're going to have z equals, the observed value is 260, the expected is 245, that is the mean. The standard deviation is 8. So 260 minus 245 is 15. 15 divided by 8, I'm going to round that to one decimal place, is 1.9. Okay, so visualizing this, because we kind of visualize with empirical rule, what's kind of going on here is I'm looking at, you have your mean at 245. We're looking at 260 or more. So we're somewhere over here at 260. I want all this area to the right. So what I did is I found the z-score of this point. Okay, I found the z-score of that point. So what I do is I'm going to go back to my table and I'm going to look up 1.9. So you go down to the ones, all the way down to 0.9. 1.9, it says 0.9713. Now, what you have to keep in mind, that 0.9713 always gives you the area to the left. So I know all of this space over here is 0.9713. That's not what we wanted. We wanted 260 pounds or more. So we're going to have to get a little bit clever here, finding this area to the right. So remember, all of this should add up to 100% or add up to 1. So if you take 1 minus 0.9713, that's going to give you the proportion of the area to the right. Therefore, you get the percentage. So 1 minus 0.9713 is going to give you 0.0287, which is 2.87%. So 2.87% is the probability that they can bench press 260 pounds or more. Our final question here, we got to figure out what's the probability that we lift between 240 and 250 pounds. This honestly is a pretty tough question, especially for folks saying like Algebra 2 that do this, but AP Stat kids should be able to knock this out. So between 240 and 250 pounds, what we're going to have to do is we're going to have to calculate a z-score for each of these values. Okay, so what it looks like visually is I'm going to have 240 at one point. Remember, this is centered at 245, and then 250 at my other point. I want to know this area in the middle. So starting with z-scores, the z-score for the 240, we actually did this up above. 240 minus 245 divided by 8 gets you negative 0.6. That's this first z-score. And then the z-score for 250. 250 minus 245 divided by 8 is going to give you positive 0.6. Okay, so what I'm going to do is I'm going to look up the proportions from my table for negative 0.6 and positive 0.6. For negative 0.6, we did it earlier. It's 0.2743. So what I just figured out is I know this area to the left of this point is 0.2743. Now, if I go look up positive 0.6, go to the 0, 0.6, see where they intersect, 0.7257. So what that represents is from this point all to the left is 0.7257. Now, what you're going to do with these is I don't want this area plus this area. That would be way too much. I just want this area in the middle. So what I'm going to do is I'm going to take this bigger area and I want to subtract off that 0.2743. That should leave me this chunk here. So we're going to do 0.7257 minus 0.2743, and that should take us to the area in the middle. You subtract those off, you're going to get 0.4514, which is 45.14%. That is the probability that a player on the team could lift anywhere between 240 and 250 pounds on the bench press. It can be a little bit tough, these problems. I kind of expect kids really to answer more of these top two. This one's pretty tough, but I still want to show it to you. Work through these, rewatch this video if you need to. That again was how to use z-scores.